the basics of linear algebra that you need to learn for AI and machine learning. In this video, I'm going to go over some of the basic concepts, explain these concepts with examples, and also tell you where some of these concepts can be applied and will be applied in machine learning and AI. I'll be using the whiteboard and live code to show you how these mathematical concepts work, and also show you how you can use the numpy library to apply these concepts in a very simple way. And I will also code some of these concepts without using any libraries or packages, so you can understand them at the fundamental level. Here's what we will be covering, but just remember that this is not a comprehensive list that you need to know for machine learning, and I will be making more videos like this to teach the mathematical concepts in machine learning. Just so you know, you can just watch me explain these concepts, but I do highly encourage you to work this through yourself. That way you have a strong understanding of these fundamentals. But as long as you can follow what I'm doing, you will understand these concepts. Remember, there's no exam here. Nobody needs to, test you on these concepts, so you don't have to memorize anything. As long as you understand this in terms of machine learning, you should be good to go. And for future videos, I'd like to know what mathematical concept or any machine learning related concept that you're struggling with. Do let us know down below in the comment section. I'll definitely make sure to respond and keep a note of what you've said. So here's a list of concepts we will be covering today. First, we're going to start with vectors and basic operations of vectors. Then we're going to look at matrices and some basic operations like dot products, determinants, inverse of a matrix. And then we will head over to eigenvalue decomposition and where eigenvalue decomposition is used, and we will also solve a system of linear equations as an example, and finally wrap it up with singular value decomposition, or SVD. I'm going to try and keep this as short as possible so that, unlike some courses out there and unlike going to college, sitting hours together in classes and trying to learn these, I hope that this video can fast track your journey in AI and machine learning. And also, while you're here, hit that like button. It goes a long way in supporting our channel. Thank you so much. So let's get started with vectors. And if this is a video that you want to watch later when you're at home or you're sitting in front of a computer so you can work through this, click the 3 dots down below and add it to your watch later playlist so you don't miss this. I know that most viewers just left, but anyway, for those of you who are here, just let me know in the comments. And just for you, let's get to it. So vectors are basically one-dimensional arrays. It could be something like 1, 2, 3, 1 row and 3 columns. In terms of machine learning, basically each data point is a vector. So what that means is, let's take the house price prediction dataset. It's basically a dataset that can be used to predict or build models that can predict the sale price or the cost price of a house based on things like area, number of bedrooms, how old is the roof, and whatnot. So each data point would technically be for one house, and that one house can be represented in terms of a vector. So if you have 100 houses, then you're basically dealing with what we call as a matrix. So you've got 100 different rows, and let's say you've got 3 features: the square feet of the house, number of bedrooms, and how old is the roof. For some reason, those are the only 3 things that I can think of. So those 3 things will be the columns. So your matrix or your data set is technically a matrix with 100 data points times 3 columns. So 100 rows and 3 columns. Vectors and matrices are basically used to represent your data. Oh, I'm blocking. Sorry about that. Basically what I meant to say is our matrix will be 100 by 3. You know what? To make sure that I don't get in your way, I'm just gonna take myself out of the equation. And if this is a series that you'd like to watch and also other videos that we make on this channel, do consider subscribing. Let's get to 5,000 subscribers. Thank you so much. Let me explain this with Python. I've already prepared this notebook so that it saves us time from typing. The first thing is I'm going to import the numpy library, which is, you can think of it as like a mathematical text-based library, which so many other libraries depend on. I'm going to show how we can use NumPy for this, how we can write a code from scratch and explain some of these concepts. Here, what I'm doing is I have v1 and v2. These are basically two NumPy arrays. You can think of them as vectors. So the first vector will be 1, 2, 3. The other will be 4, 5, 6. Now, vector addition is basically element-wise addition. We have two vectors. Basically, adding one vector with the other is adding specific elements in specific columns. I say columns here, but you get the point that this is the 0th dimension, this is the first dimension, and this is the second dimension. So you just add them up. So 1 plus 4 is 5, 2 plus 5 is 7, and then 3 plus 6 is 9. So this will be basically v1 plus v2, which when we run the cell is what we get. Dot product is something similar. Let's look at the vector dot product. So vector dot product is written as v1 dot v2. So what this means is basically you take 1 times 4, which is 4, then you take 2 times 5, which is 10, and then you take 3 times 6, that is 18, and then you basically add them all up. So that's equal to 14 plus 18, which is equal to 32. So when we run this code, basically taking the vector dot product, we get the answer as 32. Now look at what function we're using here. We're using numpy dot dot. Dot is basically a function within numpy that carries out the dot product between two vectors. Vector dot products are technically used in other concepts that we're going to cover today, so just stay tuned for that. Up next, we have the vector norm, or the magnitude of the vector. Now there are two types of norms, or actually there's more than two types of norms, but you will generally hear more about the L1 norm and the L2 norm. So let's look at what these two are. By the way, here I'm using the NumPy's Linear library, which is Linear Algebra library, and they have a norm function specifically to carry out the vector norm. And if I am correct, they use the L2 norm here. As you can see, it's also called as the Frobenius norm, which is, and they also give the formula here, it's the sum of the absolute value of your vector squared, and you will eventually, after summation, you will take the square root of this. This is really odd to see it like this, but here, let me show you on the whiteboard how this looks. Again, just to clarify, this is the L2 norm. So if we have a vector 1, 2, 3, this is considered as A1, this will be A2, this will be A3 if our vector is A. So the L2 norm is basically square root of A1 squared plus A2 squared plus A3 squared. So you can see it's a summation of the square of each element in the vector. And once you get that summation, you basically take the square root of that. So this is L2 norm. While we're here, let me explain what L1 norm is, because you will hear more about this as well. L1 norm is simply take the magnitude of A1, sum it up with A2 and A3. This is just a summation without any square roots. Also, by the way, L1 norm is called as the Manhattan norm, and L2 is also called as Euclidean norm. Now, I don't know why they have so many different names here. Maybe someone in the chat can let us know. And what you will see is norm is very useful for checking similarities between two vectors. And in a lot of applications, people do want to know how similar certain data points are so that you can, either use it for clustering or do some kind of a similarity search. And that's how norm is helpful. Okay, now that we're kind of familiar with vector operations, let's move on to matrices and some basic matrix operation. Here I use numpy.array to initialize that. And by the way, if you need an exercise, what you could do is go ahead and write a code that carries out vector norm or finds the vector norm for any given vector. Try that out yourself. So here I'm using numpy.array to initialize my matrices. As you can see, this is a 2 by 2 matrix, as in it's got 2 rows and 2 columns. So when I run this piece of code, it should technically give me row 1 is 1 and 2 for matrix A, and row 2 is 3 and 4. And for matrix B, we've got 5, 6 in row 1 and 7 and 8 in row number 2. But just remember, when you're trying to index these elements or these numbers in Python or in most programming languages, indexing always starts with 0. Okay, then we've got matrix addition. which is very simple. Again, this is element by element. So when you add A and B here, 1 gets added with 5, 2 gets added with 6, and 3 gets added with 7, and 4 gets added with 8. This is what we call as element-wise addition, which is what is matrix addition. So you can see 1 plus 5 is 6, and 2 plus 6 is 8, and the others you can always figure it out yourself. So I'm just going to run this, show you that it does do element-wise addition. And all you do is say A plus B for that. Next, we've got matrix multiplication. Now there are 2 ways to do this, and both of them have different applications. One is A times B, and the other is using dot, basically A dot B. A dot B is different from A times B when it comes to matrices. So keep that in mind. So when we've got A times B, for example, we have our A matrix here and we've got our B matrix here. When we do A times B, it is an element-wise matrix or element-wise multiplication. So it'll be 1 times 5, which is 5. Then it's going to be 2 times 6, which is 12. And then you get the point for the other 2 elements in this matrix. Whereas dot product is not the same. Dot product is different. Let me show you on the whiteboard. So here we have our 2 matrices A and B. The way dot products work is basically we have the first row and the first column here, and then we've got the second row and the second column here. So what you need to keep in mind is we multiply the elements in the row of the first matrix with the elements of the column in the second matrix. So essentially we get another 2 by 2 matrix where the first element here will be 1 times 5, which is 5, plus 2 times 7, which is 14, which is equals to 19. So what I did there is basically here we go in this direction and here we go in this direction. So we multiply them element wise and then finally add them to get the number. So that's why the first element in our A dot B matrix, if we call this as something like C, will be 19, the very first element. For the second element, what we do is multiply again 1, but this time with 6, which is 6. Then we do 2 times 8, which will be 16. And this is equal to 22. And this will be the second element in our matrix C. Then we move on to the second row here of the matrix A, and we do it with basically both the columns of matrix B. So let me just do this quickly. So there we go. We've got our matrix C. Now let's look at our code. So we're just going to run this and we get our dot product of the 2 matrices A dot B, and that matches up with what we had on our whiteboard. Now the same logic that I explained, instead of having a 1-line code with numpy, you can also write your own code, and I have written something here. You can see it's just so much bigger. What we do is basically get the number of rows and columns for both the matrices for matrix 1 and 2, and then we check if the column of matrix 1 and rows of matrix 2 are the same or not. And this is an interesting point because you can technically multiply or take the dot product of 2 matrices of different dimensions, except their inner dimension has to be the same. What I mean by this is, let's take an example here. Let's say we have 2 matrices. I'm going to scroll down here. If we have 2 matrices, one with dimensions 3 by 2 and the other with dimensions 2 by 3, then their inner dimension, which is right here, which is column of matrix 1 and row of matrix 2. So if they are equal, then the resultant matrix will be a 3 by 3 matrix after you take the dot product of these 2 matrices. So essentially the third 3 dimensions are coming from here. So if you have something like, let's say 3 by 2 matrix and another one if you have like 2 by 4 matrix, that will still work because you have the inner dimensions to be equal. So the resultant matrix will be 3 by 4 matrix after you take the dot product, that is. Also, if you're still here watching, let me know in the comments below how you rate my handwriting here, because it's awful. Going back to our code, that's what this if condition is checking for, whether or not the inner dimensions are equal. And then we're making a result matrix that basically has the outer dimensions of the 2 matrices. And then The matrix multiplication itself happens in this nested for loop. You could go through this line by line to see how exactly it works. There's also an example here that I use just to see how it works. And you can do this by hand as well. And you can see matrix 1 and 2 here have different dimensions. This is a 2 by 3 matrix, whereas this matrix 2 is a 3 by 2 matrix. And the resulting matrix has the outer dimensions of these two matrices, which is a 2 by 2 matrix. For a simpler example, I just have here a piece of code using numpy's dot method, or the dot function I should say. I'm initializing random numbers here. The first matrix L is basically of dimension 3 by 2, and the second matrix, or the matrix M, has dimensions 2 by 4, and I'm just carrying out the dot products and printing out the results. You can see the outer dimension is 3 by 4, and that's what our matrix P should be. And we can see here matrix P is basically 3 rows and it's got 4 columns. Now let's move on to matrix transpose. Matrix transpose is very simple. I'm not going to spend too much time on this because it's just that simple. So let's say we have matrix A, 1, 2, 3, 4, and basically what you do is you flip the rows into columns. What I mean by that is 1, 2 here is in the first row. Now that becomes the first column. You can see 1 here and 2 here. Whereas for the second row, again, we flip it into the second column. So we've got the second column as 3 and 4. Just flipping the row into their respective columns is basically taking a transpose of the matrix. Now let's look at a very important concept, which is the determinants. Here I'm going to use the Linear Algebra library again to carry out or calculate the determinant of a matrix A. And the function I'm using here is called DET, or short for determinant. And if I take the determinant of A, I basically get a scalar value, basically negative 2.0. But let's look at how the determinant works. Let's look at how to get the determinant of the matrix 1, 2, 3, 4. Basically what you do is take the inner cross product. Now this is not an official term, I'm just using it. This is how I learned, so I feel like it's a convenient way to explain it. So basically what you do is multiply 1 by 4, which is 4. Then you subtract it by 2 times 3. And that is 6. Notice that the order is always the same. So you always do this product first and then you do this product. And the resulting answer is -2, which is what we had on our Colab notebook. Now let's say you have a matrix that's 3 by 3, something like 1, 2, 3, 4, 5, 6, 7, 8, 9. Here comes the concept called minor. So what minor means is when you have to take a determinant of a matrix like this, you start with the first element, which is 1. The minor of 1 is basically another matrix that does not have the elements that belong to the first row or the first column. So this submatrix would be the minor of 1. So the way you get the determinant of that is basically do 1 times. And if you have these square or straight lines and numbers in it, that means this is the notation for taking the determinant. So you've got this. Then if you want to take the minor of 2, or you should take the minor of 2, and you add them up. So you do 2 times, which is don't take anything there, don't take anything there. That would be 4, 6, 7, and 9. And you do so on for every element in that matrix. And that's how you calculate the determinant of a 3 by 3 matrix. Let me explain this with some code. So here I have a function that gets the minor. So I provide a matrix for this function and also provide which row and which column to get the minor of. So basically what it does is it checks for all the elements that does not belong to that particular row and that particular column. As an example, instead of, going through each bit here of the list comprehension, let's look at an example here. I'm using the function getMinor on the 2 by 2 matrix that we have here, which is basically 1, 2, 3, 4, and then specifying the indices of 1, which is 0, 0, and just printing that out. Let's see how that works. So when I run it, it says that particular minor M is 4. What that means is if you have 1, 2, 3, 4, then you don't take anything in the row of 1. Basically, that results in the element 4. Now, if you want to do that for the 3 by 3 matrix here, let's go ahead and do that. I'm just going to put 3 by 3 there. And again, let's just stick with 0, 0. I'm also going to go ahead and print the two matrices that we have so that we can see what these things actually are or how they look like. Matrix 3 by 3. So there we go. And when we print that, we have something like this. So nothing of the first row is taken and all the elements in the first column, which is 4 and 2, is omitted. So technically we have -2, 5 and 8, 7, which is what we have here. So that's what the miner does. And we can use that function to carry out or calculate the determinant. For the base case, we do have a special case where we technically don't need the miner. So we just calculate the determinant here and return it. And for higher order matrices, we basically calculate or get the miner first and then do something that's called as cofactor. This cofactor, depending on what the column is or the column value is, if it is an odd number, then your cofactor will technically be -1. If it's an even number, then it will be +1 because we're taking the power of it. Now that I see it, I think I made a mistake on the whiteboard. So let's go back. Here it was. So we've got the 0th column, we've got the first column, and we've got the second column. So technically the way it works, let me erase this and actually do the whole thing and show you so we don't mess up anything this time. So this 1 is actually not just, 1 times the miner. It's actually -1 to the power 0 times 1. And anything to the power 0 is basically 1, and 1 times 1 is 1. That's why we have that. And here's the mistake I made. This is not a positive sign. This should be negative. So let's go and change that. And the reason is this 2 is actually -1 to the power 1 times 2. And that's -2. And similarly, if you want to do for 3 here, so our miner becomes 4, 5, 7, 8. And then let me just erase this plus for now. It's going to be -1 to the power 2 times 3. And this whole thing is equal to 3. So we're just going to go change that here, make it as +3. And let's go take determinants of these minors and check what the final determinant looks like for this 3 by 3 matrix. So that's going to be 1 times 45. I'm going to do it like this, minus 6 times 8, which is 48, minus 2 times, I'm right here, 4 times 9, which is 36, minus 7 times 6, which is 42, plus 3 times 4 times 8, 32, minus 7 times 5, which is 35. And when we do all the math here, this should result in 0. So that's the determinant, and that's how the determinant works. So you can see when we do the calculate the determinant of our 2 by 2 matrix, it's basically -2, and the determinant of 3 by 3 matrix is about -306, and that is for this determinant. And if you're curious, you can do this by hand and check it out yourself. Next, let's move on to inverse of a matrix. The condition for carrying out or calculating the inverse of a matrix is we should not have the determinant of that matrix to be equal to 0. So the matrix we just use on our whiteboard cannot be used to calculate the inverse of that matrix. Or basically, in other words, you cannot calculate the inverse of that matrix that we just used. So what exactly is inverse? Here we're using the INV function from Linear Algebra just to simplify everything, but let's look at this on our whiteboard. Before we move on, it is important to note that inverse of a matrix is very important in terms of numerical computation when it comes to building artificial neural networks. This concept is used in solving a system of linear equations, which is what is needed to determine the weights in our neural network. So if we have a matrix A and we call its inverse as A minus 1 here, then technically speaking, inverse of A times A is equal to what's known as the identity matrix. An identity matrix example is for a 2 by 2 identity matrix. Its diagonal elements are basically 1 and every other element is zeros. This is one of the properties of an inverse of a matrix. Now there are a couple of different ways of calculating the inverse of a matrix. One particular way that I will show here is what's called as the adjoint of the matrix A divided by the determinant of the matrix A. So let me explain what this is. You already know what the determinant of the matrix is. Now let's look at what the adjoint of a matrix A is. Transpose of the cofactor matrix. So what is this cofactor matrix? So let me explain what this cofactor is. For example, let's take a 2x2 matrix A, B, C, and D. First thing is we calculate the cofactor. So what the cofactor basically is you take the minor with respect to each element in this matrix. The minor of A is D. Then the minor of B is basically C. Minor of C is B. And minor of D is A. We already know how to get this from earlier in the video. So we've got the minor matrix. Let's call it M, and we're just going to call this A. Now what you do is multiply M by basically either plus or minus sign depending on the index. So what that means is, if you remember from before, we had -1 to the power I or j, whatever the ij value was, or technically it's I plus j when we were looking at calculating the determinants. So for the very first element D, it's 0, 0, so it's -1 to the power 0, so that will be plus, which is D. For this, for C, element C here in the minor matrix, this will be 0, 1, which is I is 0, J is 1, so that will be -1, so or minus C. And B is also multiplied by -1 to the power 1. It's indexed as 0, 1, or sorry, 1, 0, so that will become minus B. And then we've got A as 1 plus 1 here, which will be -1 to the power 2, which is plus, so this will be A. This here is our cofactor matrix. Now to find the adjoint, we just take the transpose of this, which is going to be something like D minus C minus B A. Now let's say we have a 3x3 matrix, and you can try this on your own, but the only thing that you need to keep in mind is your cofactor matrix here will not be one element each. It'll technically be the determinant. What I mean is technically it will be the determinant of the minors. So if you've got something like, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. By the way, you cannot take the inverse of this matrix, or it's basically undefined, because remember the determinant of this matrix was 0. So if we look at our formula for inverse, this will basically be divided by 0, which is not defined. So just keep that in mind, but I'm just going to show this as an example. So here your minor matrix is going to be 5, 6, 8, 9, which is the determinant of that. And then you've got to have, for the second element in the first row, that's going to be something like 4, 6, 7, 9, and so on. So you will have a huge minor matrix with where you have to calculate the determinant of each of these. So I'm not going to do this by hand, but instead let's go to our code. So here I'm using the inverse function from the numpy Linear Algebra library, and I do need to have this exception where, you know, if there's a Linear Algebra error, which is basically defined as dividing something by 0, which is not determined, then it will basically say matrix A is singular and does not have an inverse. So when we run this code, we basically get the inverse of our matrix A, which if you remember was basically 1, 2, 3, 4. Okay, now we've got the inverse. Let's look at how to do eigenvalue decomposition. Eigenvalue decomposition is taking a matrix and decomposing it into its respective eigenvalues and eigenvectors. And again, as you can see, the numpy library just simplifies this for you. There is an Eig function that carries out the eigenvalue decomposition. So if you want to do this for our matrix A, I just run this code. It gives us the eigenvalues for the two eigenvectors. Remember, we've got two vectors here and we've got two eigenvalues here. So these eigenvalues corresponds to these vectors. Now let's look at this a little bit more closely. Eigenvalue is how much a matrix stretches or shrinks in a particular direction, and this direction is given by the eigenvector. So that's the difference between eigenvalue and eigenvector. And what you will notice is, as I explain this, eigen decomposition is basically done to understand your data better and also at the same time reduce the dimensionality of your data. If your data has too many features, something like eigenvalue decomposition, or which you will learn soon about things like singular value decomposition and PCA, these are methods that's used to reduce the dimensionality of your data set. So let's look at how this works. So eigenvalues are basically solutions to a given set of equations that are defined by the determinant of a minus some factor lambda, which I'll talk about what lambda is soon, times the identity matrix equals 0. So let's just say A is some matrix 2, 1, 1, 2, and if we put this in this above equation, we basically get something like determinant of A, which is our matrix 2, 1, 1, 2, times or minus lambda times our identity matrix, which is something like this, and this will be equal to 0. So just doing some math here, the determinant of what we're trying to figure out is 2 minus lambda. We've got 1 here and then 1 and 2 minus lambda. So this is basically what we are trying to find the determinant of. So when we do write the equation for our determinant or reduce this to the equation, it's basically 2 minus lambda squared, because it's 2 minus lambda times 2 minus lambda minus 1 equals 0. I'm doing a little bit of math ahead in my head here. This will be lambda squared minus 4 times lambda plus 3 equals 0. And solving this equation, basically minus 3 equals lambda times lambda minus 4, something like this. Sorry, cut you off there. So the lambda values that will satisfy this particular equation is, there are two values. One is 3, and I'm going to call it lambda 1, and lambda 2 is going to be equal to 1. So these are eigenvalues. Next, using these eigenvalues, what we do is solve for our eigenvectors. So we use that a minus 3i, which is this 3, and we multiply this by our eigenvector, let's call it v, equals 0. And then the other equation would be a minus I times v equals 0 again. Now, when you do this math a little bit, what you're going to get is v1. I'm going to call it v1 and 2. This v1 is 1, 1, and v2 is going to be equal to minus 1 and 1. You can work this out, substitute our matrix A and I here, and you will figure it out. So then comes our eigen decomposition. What we can say is, given any matrix A, we can write this as something like our eigenvector V times our diagonal matrix, something like that. I don't know what that is called, but that's how we represent it. And then that times V inverse, where V is the eigenvectors. And in this case, V would basically be a combination of these two, which is 1, 1, minus 1, 1. I'll use some distance there, 1 and 1. So that's going to be our eigenvector V. And this guy here, which we can call it as capital lambda. If there's a name, let me know in the comments below. That will be a diagonal matrix of our eigenvector, or sorry, eigenvalue. So our eigenvalue is basically 3 and 1. So it'll be the diagonal matrix of that. So now we've taken our matrix A and decomposed it into our eigenvalues or eigenvectors and eigenvalues. So an example of this concept is in applying principal component analysis, which we will look at in depth in an upcoming video. So don't forget to hit like and subscribe if you're still watching at this point and if you've enjoyed this type of explanation. Thank you. So that's our part on eigenvalues and eigenvectors. Next, moving on to solving a system of linear equations. Let's say we have a system of equations ax equals b, where a is another matrix and b is a vector or another matrix. So if we are to solve a system of equations like this, for example, we have this code block here. All we do is use the numpy's dot solve to get us the solution, which is x, and this is very commonly used in linear regression, and which is why I want to show this concept because it's really important. So let's say we have a matrix 1, 2, 3, 4 like before, which is our A matrix, and let's say we have a target which we call as B in this case. And in terms of like, if you think in terms of machine learning and data sets, let's say this matrix A technically represents our house price prediction data set. And the price of the house or the cost of the house is basically our target. In this case, it is B. So the first house has these two features, 1, 2, and its price is 5. The second house has some two features, 3, 4, and its price is 7. I really wish houses were as cheap as $5 and $7. No, actually, I don't wish that. But anyway, for this set of equations, the value of x that we need to find is minus 3, 4. Now, digging into this dot solve is going to take a lot more time and probably another entire video on its own. So I'm just going to let you figure that out for yourself for now. But I just wanted to show you that we do have something like dot solve to solve a system of linear equations. Next, we move on to our final topic, which is singular value decomposition. Now, instead of going to the whiteboard here, I will just briefly explain what this is, because a lot of the steps involved here is something that we have already done. So let's explore that. So here's the steps for singular value decomposition. What you need to do is, for a given matrix A, you need to calculate its A transpose A and A times A transpose to get the eigenvectors and eigenvalues. The eigenvectors of A transpose A is known as the right singular vectors, and the eigenvectors of A transpose is the left singular vectors. Basically, we call it as V and U. And the singular values are the square roots of the eigenvalues. So whatever eigenvalues you get by computing these quantities for your matrix A, taking the square root of those values are basically the eigenvalues. And those eigenvalues are placed in the diagonal matrix. And to reconstruct the original matrix, what you basically do is take the left singular vectors times the diagonal matrix of the eigenvalue and the right singular vector transpose, and that will regenerate your matrix A. So linalg again has a simple function called .svd, which basically decomposes your matrix, carries out singular value decomposition on your matrix A. And what it gives is three quantities, U, S, and Vt, where U is our left-sided singular vectors, and Vt is the transpose of the right singular vectors, and S is basically the singular values. So when you do that and print this, what you will see is for our matrix A, which is 1, 2, 3, 4, we get the U matrix and we get the transpose of the V matrix, and we also get the singular values.